What's up, guys? Today we're going to be talking about, this is 6.4. I don't know why it's not on my slide, but there it is, 6.4, and we're doing applications of linear systems. This is a really helpful kind of chart to copy down, so make sure that you pause and copy this down. So choosing a model for solving linear systems, we've looked at 3 different models thus far. We've looked at graphing, we've looked at substitution, and then recently we looked at elimination. And this tells you when you would want to use these things. So graphing is going to be best to use when you want a visual display or you want a quick estimate of a solution. I think I mentioned in one of the other videos, it's not super accurate. These two are specifically accurate. So if you're looking for accuracy, you do not want to use graphing. Substitution is one to use when the equation is already solved for one of the variables, or it's easy to solve for one of the variables, meaning that it has the assumed coefficient of 1. So you either have something where it's like y equals 3x, or you have something where it's like x plus 4 equals 7y. Well, it'd be easy to solve for that x by subtracting 4. So in those cases, substitution is probably going to be your best bet. Eliminations when the coefficients of one variable are the same or opposites, or it's not convenient to use graphing or substitution. So this is the fallback. All right, so I check substitution first, and if that doesn't work, you go to elimination. And these are your 3 methods to solve a system of linear equations. So here's the deal. Oh man, it's 3 in the morning. I should really get off the computer and go to bed. This is a lot of you, except you guys don't have the facial hair like that. But someday you might. And then you go and your mom's like, hey, you need to put down your computer, and then you go to bed, and then here's what you do. An hour later on your phone. Yeah, you know that's you. You need some shut-eye. I see the dark circles under your eyes just like this dude. Okay, finding a break-even point. Make sure you copy this into your notes. A break-even point for a business is the point at which income equals expenses. So if you start a business, if you're selling teddy bears, it costs you money to sell those teddy bears. So if you have 100 of those teddy bears made, there's a particular cost for that. You haven't sold anything. So let's say this is our teddy bears. All right, it costs us this much money to make them. All right, so now I have the teddy bears. The more I make, the more expenses I have to pay to continue making those teddy bears. I don't make any money until I sell my first teddy bear. So there's my first one, then my second. The money that comes in for your income should be higher per teddy bear. In other words, the slope is greater per teddy bear than the expenses per teddy bear. So the expenses should not increase as quickly as the income, even though the expenses start at a higher point. So at some point, you continue going and the income becomes greater than the expenses. So everything that's on this side of the graph, you are losing money. But everything that's on this side, you start making money. When those two things switch is called a break-even point, which is what that is. Break-even points are good, but you want to be over here where you're making money. We could use systems of equations to find that. So here's the problem. It says a fashion designer makes and sells hats. The material for each hat costs $5.50. The hats sell for $12.50 each. The designer spends $1,400 on advertising. How many hats must the designer sell to break even? So the first thing, we're going to have an income equation, and then we're going to have an expense equation. I usually just label them like this so that I know what's what. Okay, the material for each hat costs $5.50. So that's an expense item. It's $5.50 per hat. I'll say 5.5 H. The hats sell for $12.50 each. That's an income. So 12.5 per hat. And then the designer spent $1,400 on advertising. That's an expense. So I'm going to add that expense to the cost per hat. All right, so I have income and expenses. A break-even point is when the income equals the expenses. So in order to solve this, I'm going to set these two equations equal to each other. So I have 5.5H plus 1,400 equals 12.5H. All right, so when income equals expenses, or income equals, sorry, I said that backwards, but you get the idea. All right, so first thing I need to do is isolate my H, get it by itself. So we'll subtract 5.5H from both sides. My apologies. for writing that wrong first. So 1400 equals 7, excuse me, H, divide both sides by 7, and 14 divided by 7 is 2 plus the 2 zeros. So the number of hats that need to be sold is 200. Now what this means is that at 200 hats, the income is equal to the expenses. If they sell less than 200 hats, that means they're losing money. If they sell more than 200 hats, they're making money. So again, this is where you break even. Here's one that's similar for you to try. Actually, no, it's not. We don't have work through examples on this one. This is just applications. So let's take a look at this one. Identifying constraints and viable solutions. So there's sometimes when a math problem doesn't make sense. And that's what a constraint or is a solution being viable is all about here. So let's go ahead and look at this. It says the local zoo is filling 2 water tanks for the elephant exhibit. One water tank contains 50 gallons of water and is filled at a constant rate of 10 gallons per hour. The second water tank contains 29 gallons of water, is filled at a constant rate of 3 gallons. When will the 2 tanks have the same amount of water? Okay, so I have tank 1, contains 50 gallons, and it grows at a rate of 10 gallons per hour. So we'll just say 10 gallons per hour. The second water tank, I guess that should be an H. Let's make it an H. It'll make me feel better about myself. Dink. And give me my marker back. There we go. All right, 10H. And then tank 2 contains 29 gallons of water and fills at a rate of 3 hours per gallon. All right, so I want to know when will the 2 tanks have the same amount of water? Well, in order to solve this, I just set these 2 things equal to one another. So 50 plus 10H. I want to know when is that the same as 29 plus 3H. And then I go through and I solve my equation. So let's get the variable on the same side. So 50 plus 7H equals 29. And subtract 50. And I get 7H equals negative 21. Divide both sides by 7. And I get H equals negative 3. Now that mathematically should be fine to you. But you should look at that and think, wait a second, that doesn't really make sense. Negative 3 hours. When will the 2 tanks have negative 3 hours? All right, so we're going to go back in and substitute that back in here. I just want to show you something real quick with that. So if we wanted to solve for how much water would be in there, I would put this negative 3 in here. So I have 20 or 50 plus 10 times negative 3, which would be 50 plus negative 30. I know I'm doing this mental math, but it's for the sake of time. So it'd have 20 gallons of water in it, and then this is negative 3. This is called a non-viable solution because how do you have negative time? All right, so when will the 2 tanks have the same amount of water? It's non-viable because you can't have negative 3 hours. It doesn't make sense. Now, you may be able to use this and think to yourself a little bit, well, if I go back in time 3 hours, maybe they would have the same solution, and that's a little bit different. But in terms of the way it's solving this system, having negative 3 hours does not make sense. So we'd say that that solution is non-viable. Let's look at another one here. Solving a wind or a current problem. It says a traveler flies from Charlotte, North Carolina to Los Angeles, California. At the same time, another traveler flies from Los Angeles to Charlotte. The airspeed of each plane is the same. The ground speeds are shown below. What is the airspeed? If air flows this way across our country, and you're flying with the airspeed, that means you will fly faster than somebody that's flying against the airspeed. If you've ever been at the airport and they have those moving walkways, you could walk 3 miles per hour on one moving walkway. And if you're walking with it, so let's say you are walking 3 miles per hour, and the moving walkway, I'll call that MW, is going 2 miles per hour. If you're walking with it, then you would be going 5 miles per hour. You would add your speed to that. If you're going against it, then you would be going a total of 1 mile per hour. You'd be going very, very slow because your 3 miles per hour would be subtracted by 2. You're going against it. So that's called ground speed, and that's what these things mean right here. Okay, so how fast is the actual ground speed? Well, the ground speed is the same as the walk speed here. Okay, airspeed is going to be a. So we want to find the airspeed of this plane going across the country. Again, it works very similar. I think the walkway thing is a little bit easier to wrap your mind around than an airplane flying through the air. So the first flight is going this way. The ground speed is how fast they're actually moving. So that was that 5 miles per hour and 1 mile per hour that I just showed you here. I know that the airspeed is A, the wind speed is W, so the airspeed plus the wind speed gives me a total speed of 550 miles per hour. That's going from Los Angeles to California. I'm going the same distance here. To go from Charlotte, or North Carolina, to Los Angeles, I'm going to have my airspeed, how fast the plane is going, but this time I have to subtract the wind speed because I'm going against the wind. So it actually makes me go a little bit slower. It's going to take a little bit longer to get there. And any of you that have ever flown across the country have probably experienced that. So here are my two equations. So this is Los Angeles to Charlotte. This is Charlotte to Los Angeles. Notice it sets up very nicely for elimination. I could add straight down and it eliminates these W's. So I have 2A equals, add these two things together, 1045. Double check that. It sounds, yeah. And then I would divide both sides by 2. And I get an airspeed of 522.5 miles per hour. That is how fast the airplane is actually traveling. All right, 522.5 miles per hour. You could find the distance by substituting this in if you wanted, or you could find the actual wind speed. It's not absolutely necessary, but this is how you would find how fast the actual plane is going. What is the airspeed? Be careful, because sometimes you are asked for the wind speed on this. But again, you set this up like this. These are walkway problems. This is you're rowing a boat down the stream with the current, and then you're rowing it against the current. All of those problems set up this way. And that's it. So I will see you in class. Hopefully you took good notes.